Hello students. So today we will start our next topic, which is divergence of a vector field. Earlier we did gradient of a scalar field, and now we will do divergence of a vector field. This nomenclature is very important. Okay, we will discuss it later. Okay. So divergence of a vector field is defined as the dot product of del operator and the given vector quantity. Okay, and del operator, as we already know, is given by this reverse triangle with arrowhead on it, dot a vector. Okay, and this del operator need not to be have vector always on its head. Okay, if we do not put that arrow on its head, even then it is considered to be a vector quantity. For the simplicity, we always use a reverse triangle as a del operator, which by default considered to be a vector quantity. Okay, and del, as we already discussed in our previous lecture, is given by I cap curly over curly x plus j cap curly over curly y plus k cap curly over curly z. Okay, and a vector is equal to this ax I cap plus ay j cap plus az k cap, and divergence of a vector field is nothing but the dot product of these two vectors, del dot a. Okay, which will become this. So del dot a will become this value, curly over curly ax plus curly over curly y plus curly az over curly z. Okay, so as we already know, the dot product of any two vectors is a scalar quantity. So here both are the vectors. Del is a vector quantity, a is also a vector quantity, so its dot product will also be a scalar quantity. Okay, and because it is a scalar quantity, so it can have positive values, negative values, or zero values. Okay, now we will define mathematically how we define divergence of a vector field at a point. Okay, this wherever we have defined these terms, either gradient of a scalar field or a divergence of a vector field, you need to remember one thing: we always define these terms at a particular point in that given field. Okay, that you always need to remember. Okay, you are discussing the properties of a particular point in the given field, how that is behaving. Okay, so mathematically the divergence of a vector field A at a point is defined as the volume limit of its surface integral per unit volume as the volume enclosed by the surface tends to 0. Okay, this we will discuss later. So mathematically, just you need to remember how do we write this term. So divergence of A means del dot A will be equal to limit delta V tends to 0, where delta V is nothing but the volume element, small volume elements. Okay, 1 over delta V, again it's volume, small volume, surface integral A dot n cap ds. Okay, so mathematically this is how we define this divergence of a vector field at a particular point. Okay, so now we will discuss its physical significance. Okay, physical significance of divergence means what? Physically, the divergence of a vector field represents the net amount of flux linked per unit volume evaluated at a point where the volume enclosed by the closed surface around the reference point is taken to be infinitely small. Okay, see how we have defined this. The physical significance of divergence, it is nothing, it is again the net amount of flux linked per unit volume. Okay, amount of flux per unit volume evaluated at a point, because again we define these quantities at a particular point, divergence at a point. Okay, so around that point, how much flux per unit volume is there. Okay, and around that point we have considered a volume enclosed by the closed surface around that reference point is taken to be infinitely small. Okay, for a very, means we have considered around that reference point a small area, okay, which is infinitely small, and in that infinitely small area volume will going to be small. Okay, so within that area, whatever be the volume is there, from that volume how much flux lines are coming out per unit volume. Okay, that is our divergence of vector field. That is nothing but the divergence of vector field. Okay. So further we'll to further explain this physical meaning of divergence. Okay, let us consider some incompressible fluid like water is flowing through infinitely small parallel pipette with sides dx, dy, dz as you seen in this figure. Okay, as you seen in this figure, we have considered a parallel pipette having sides dx, dy and dz. Okay, along x, y, z axis, and let a be the value of the vector field at the center p of the parallel pipette. Okay, at this point, at the center of this parallel pipette, we have considered a point p where the value of vector field is a, and let us consider this vector field a has components along x, y, z which are ax, ay and az. Now if curly ax over curly x is the rate of change of ax along x axis, okay, and if we move from this point p to this point r, okay, this point is our r, okay, along the positive direction of x, because this parallelepiped has the total dimension dx and p is the center of this parallelepiped, therefore this p to r will be 1 by half dx. Okay, p to r will be 1 by half dx, this value. Okay, this will be 1 by half dx. So the change in the value of ax from p to r, okay, at p the vector field has x component ax, okay, but when we move from p to r the x has changed, so the component of ax will also get changed. How much it will change? It will be equal to this curly ax over curly x into half dx. Okay, so the total change in x component of a at a point r will be this value. This will become ax plus 1 by half curly ax over curly x into dx. Okay, similarly if we consider point q, which will be this at this face, okay, which lies along the negative direction of x with respect to point p, because p is at this point. Okay, so therefore the total component of x along x component of a at point q will be this will be ax minus 1 by 2 curly ax over curly x dx. Okay, now since the flux through any small area is given by the product of area and the normal component of vector on this area, okay, this we already discussed in our earlier lectures. Okay, the total flux through any surface will be nothing but the we will take the normal component of that vector through that surface. Okay, so if we calculate the flux through the face EFGH, okay, see this face EFGH, through this surface if we calculate the flux in outward direction, then it will be the component of a at this point r will be, we have already calculated, which is ax plus 1 by 2 curly ax over curly x dx. Okay, and the multiplied with the area of this face. So this face is along in yz plane. Okay, so yz plane, these sides will be ef will be dz and eh will be dy. So area of this face will be dy dz. So the flux will be the value of that vector at point r into this area dy dz. Similarly we can write the flux through the face ABCD, A, B, C and D. Okay, through this surface the total flux will be this. We know the component of A at point Q, okay, which is ax minus 1 by 2 curly ax over curly x dx, and again this face is in yz plane, so the area will be dy dz. Okay, so we have seen the flux is positive when vector is in same direction as the outward normal, and flux is negative when it is in opposite direction. Okay, so if we calculate the net flux leaving or diverging from the parallelepiped along x direction, okay, if we calculate it along x direction only, okay, the net amount of flux which is diverging along x axis, that will be the sum of these two. Okay, the flux passing through that surface EFGH and the flux which is coming towards the face ABCD. Okay, so net flux will be sum of these two. So when we solve this term, okay, what we get the first term, this AX dy dz, and in second term here minus AX dy dz, this will get cancelled out, and what we will end up, we have this value curly AX over curly x dx dy dz. Okay, this is what, this is the net flux leaving or diverging from the parallelepiped along x axis, along x direction. Okay, so similarly we can calculate this net flux leaving through the parallelepiped along y and along z axis. That will also be given by like this, curly along y it will be curly ay over curly y dx dy dz, and along z it will be curly az over curly z dx dy dz. Okay, so if we calculate the total flux diverging from the parallelepiped having volume dx dy dz, okay, earlier we have calculated the flux diverging from a particular direction. Okay, now we are calculating the total flux diverging from the whole parallelepiped. Okay, that will be sum of all these three. Okay, so that will become this value, curly ax over curly x plus curly ay over curly y plus curly az over curly z into dx dy dz. Okay, so further if we calculate this is the total flux diverging through that whole volume, and if we calculate this total flux per unit volume, okay, net flow per unit volume will be this dx dy dz is the volume, so that per unit volume total flux per unit volume will become this value, curly ax over curly x, curly ay over curly y, curly az over curly z, okay, which is nothing but the divergence of vector A. Okay, so divergence of vector A is physically what it is, what is the physical significance of divergence of any vector quantity, what it is nothing but the net outflow per second per unit volume. Okay, the physical meaning of divergence of a vector function is that it gives us the net outward flow per second per unit volume of the surface at a given point. Okay, so now we have many examples of many special cases regarding this divergence of a vector field. Okay, as we already discussed, because both are the vectors and dot product of these two. Okay, so the ultimate result will be a scalar quantity, so it can be a positive, negative and 0. Okay, and suppose in any case if we have divergence of any vector is positive, that means what, our fluid is expanding. Okay, okay, divergence of A is positive, that means our fluid is expanding and it works as an source. Okay, so example of that is this curve. Okay, the electric field lines from a positive source is diverging out. Okay, so the divergence of a positive charge, electric field of positive charge is positive always. Okay, and if divergence of any vector is negative, it shows that fluid is contracting at that point. Okay, the example of this is this thing. For a negative charge, the electric field lines seems to be like this. Okay, means they are coming inwards towards that point, means that fluid is contracting at a particular point, or it will working as an sink. Okay, means things are coming and they are draining into that point. Okay, another example, if divergence of a vector field is 0, that means around that point, okay, it neither has a source nor a sink at that point. Okay, so the fluid is incompressible. Okay, like this, around this point if we see, so what is happening, the number of field lines which are coming towards this point is equal to the number of field lines which is going out from this point. Okay, so the net outflow is 0. Okay, the example of this is del dot b is 0. Okay, the divergence of a magnetic induction is always 0. That means magnetic lines of force form the closed curve such that these vector fields are called solenoidal fields. Okay, if we have any vector field having divergence of that vector field is 0, means those vector fields are solenoidal fields, means they do not have any source or sink. I hope you have understand the concept of divergence of vector field. Okay, and related with this we have another topic which is very important,